All right, there's something that David brought up about this paint, Vanta Black. So this is blacker than the original Vanta Black. Vanta Black is a world record for black paint. See that? It's weird.
Oh, because it absorbs all colors.
Yeah, you see a black body, it would absorb all colors of visible light. Oh, that's weird, isn't that? So it's absorbing all that light.
What applications does that have?
Applications? I was thinking it has military application maybe or something like that.
That's the only one.
So if it's absorbing our light,
Over it.
so if it's absorbing all that light, what happens when it releases that light? Because technically, then, would the electrons?
Technically, there are different ways that it could release it. One way is it could release it as heat, so it just gets warmed up.
So
Yeah.
would that most probably be releasing it by heat?
Yeah, this wouldn't be a probably good black body emitter. It's probably just releasing it as heat.
Okay.
Oh, that's really weird.
It's like Onyx Platinum.
I'm sure NASA has been developing super black materials. I have to read this. I'm sure there are applications.
Can they work with like solar panels?
No, the problem is it makes heat rather than
Experiments for like.
Vanta Black in space.
Oh, that's in space.
No, this is insane.
She worked with like.
The sculpture.
Doing like the basic. You know, like
You
basic.
can make a Dyson sphere out of that.
They take it all. They like slavery.
I'm saying like you can just make
They like work like the PhDs. They like. Yeah.
also it's
Like slave.
Let's see if this shows.
Oh yeah, this is one Our final is a third of our grade anyway, so.
Okay, here we go.
So, and it replaces the lowest test score, so.
3D printed bluestone with bronze paint.
But my last test was the lowest score.
Midnight, it's like bronze sash. Oh,
What?
3D painted bluestone with BB.
can't even see his face.
Wait, I don't get it.
Is that weird or what?
It like eliminates like contours.
It's so weird.
It's a big good camouflage.
But as soon as you turn it around, it'll show up. Oh, because you don't see
Like really hot.
Like you don't see the actual texture like that, the facial like
Yeah. Pretty weird.
It's crazy. It's tricky.
Yeah, that is weird. All right. So, okay, so let's review a little bit about the development of quantum.
Yeah, like that's what I don't get. Like it's like the basics. If I get like everything up to like something like 0, 1.
Quantum mechanics is the theory that underlies chemistry as well. So we'll talk about the development of quantum mechanics. The development of quantum mechanics started with observations. What was the observation that led to the development of quantum mechanics?
It's the hydrogen light.
The hydrogen what?
The hydrogen, the spectrum. Like it didn't show the whole spectrum.
Yeah. The hydrogen atom spectrum.
And then Bohr's theory only worked for
Yeah.
elements with one electron.
Well, what about the hydrogen atom spectrum? Why did the hydrogen atom spectrum lead to quantum mechanics? It's because it didn't turn out as expected. The hydrogen atom was expected to be what?
To show the full spectrum.
Well, we call that what? If it shows the full spectrum, we call it I mean, this is
Black
what
body.
a black body emitter. The hydrogen lamp was supposed to be a black body emitter, and it would absorb too that radiation. But it wasn't. It was expected to be black body. What we ended up getting is forbidden and allowed. And so, it was expected black body. And that would be a great black body right there. But was observed. In the black body, it absorbs all energy, so the continuum of energy is absorbed. But what was observed, not a continuum. What was observed is there were allowed and forbidden energy. That was a unusual observation. The observation led to some pattern, which is we call the line spectrum. That pattern led to a law. What was the law that resulted? Called or how about the equation? What was the name of the equation? Rydberg, good. We have the Rydberg law, the Rydberg equation.
R sub H.
Yeah. I'm not gonna write it out. That led to a hypothesis. The hypotheses were that these allowed energies corresponded to orbits. We had allowed orbits and forbidden orbits. And then we ended up with the Bohr theory. The Bohr theory with orbits, electrons circle the nucleus in orbits, turned out to be wrong. And so the Bohr theory was abandoned. In fact, this whole idea of orbits was abandoned. It's wrong. But the idea of allowed and forbidden energies was retained because the Rydberg equation is not based on any theory. The Rydberg is just an empirical equation. The Rydberg equation is fine. It's totally valid. And so this was abandoned. And then two developments led to quantum mechanics. What were those developments?
Orbitals. Yeah.
Yeah, one was de Broglie. De Broglie did what? And the other was Heisenberg. Heisenberg did what? What was de Broglie's contribution to the quantum mechanical model? I mean, this is that's actually critical.
So you couldn't,
Yeah.
we don't even know the energy, kinetic position.
That was Heisenberg. Yeah, wave particle.
Yeah. De Broglie had the wave-particle duality. That is, matter has wave properties. And Heisenberg had the uncertainty principle. And so we retained this, this idea of quantized energies. Quantized energies are their allowed energies and forbidden energies, rather than continuous energies. So we retained that from the Bohr model, but the Bohr model, this whole idea of orbits is wrong. In quantum mechanics, we talk about orbitals rather than orbits. This is our modern day theory. So let's take a look at de Broglie and Heisenberg in a little bit more detail here. And then talk about the quantum mechanical model. The quantum mechanical model, orbitals, is based on, the Schrodinger equation. Because if we combine all these factors, we end up with Schrodinger equation. Well, if matter has wave properties, we have to factor those wave properties in. And so we'll take a look at de Broglie first. The de Broglie equation is not difficult. De Broglie says lambda of matter is equal to h over mass times velocity, mu. And so we could do a calculation here. Example would be an electron with a velocity equal to 3 times 10 to the 7 meters per second. So we'll have an electron going 1/10 the speed of light. What would the wavelength be? And so to calculate the wavelength of the electron, we need h, which is 6.626 times 10 to the minus 34 joules times second. We need the mass of the electron. Mass of the electron we could look up. It's going to be 9.11 times 10 to the minus 31 kilograms. And we'll need the speed, which I gave 3 times 10 to the 7 meters per second. So let's take a look at the units. The units don't seem to work out, except we should know the definition of a joule. The definition of a joule is what? A kilogram meter squared per second squared. And so when we look at that definition, then the units do work out, because the kilograms will cancel. One of the meters will cancel, one of the seconds will cancel, the other second will cancel. And so we'll be left with meters. So let's go ahead and calculate the wavelength of this in meters. The 6.626 times 10 to the minus 34 divided by 9.11 times 10 to the minus 31 divided by 3 times 10 to the 7. Okay, the wavelength comes out to 2.424 times 10 to the 369. Times 10 to the minus 11 meters. So that would be the wavelength of the electron. And that, let's get that in. This would be 24.24 times 10 to the minus 12 meters. 10 to the minus 12 meters. 10 to the minus 12 is called a what? Pico. So this is 24.2 picometers. 24.2 picometers, well, this would be the same thing as 0.242 times 10 to the minus 10 meters. 10 to the minus 10 meters is called an angstrom, so this would be 0.242 angstroms. The 24.2 picometers or 0.242 angstroms, which is about how big? How big is that? It's pretty small, but
So less than because of that,
how big is that compared to something you know? What can you compare that to?
to an atom.
To an atom. And so compared to an atom, how big is it?
The smallest atom is 1 angstrom, so
Yeah,
it's like a
smallest
fifth.
atom's 1 angstrom, so this would be about a quarter
fifth
of the size of the smallest atom, which is hydrogen. And so this is about, the wavelength is about on the order of a little smaller than the atom. Okay, let's do another one. Let's do baseball. Baseball is a piece of matter. So we'll do baseball with a velocity of 60 miles per hour. Well, I have to make sure the units work out. To make sure the units work out, I need to determine the baseball mass in kilograms. The baseball mass off Wikipedia is 0.145 kilograms, or 145 grams. And then I need to convert 60 miles an hour to meters per second, and I don't want to do it by hand, so I'll just do it. 60 miles per hour to meters per second. It's 40.2.
Nice.
Oops.
I mean, that's accurate too.
It's 26.8. So this is 26.8 meters per second. So let's go ahead and calculate the wavelength. The wavelength of the baseball matter is going to equal 6.626. This you don't have to memorize. This Planck's constant will be given, divided by the mass, 0.145 kilograms, divided by the velocity, 26.8 meters per second. And this should give us units of meters. Let's go ahead and calculate this one. So this is going to be 6.626 times 10 to the minus 34. Divided by 0.145 divided by 26.8. And I get a wavelength of 1.705 times 10 to the minus 34 meters. So 10 to the minus 34 meters, that's, how big is that? That's way smaller than an atom, isn't that? That's incredibly small. In fact, I kind of remember, didn't we have something like that when we were talking about light the other day? That is, what kind of light would that be?
It'll be red. Ultra.
Ultraviolet? Red?
It would be ultra violet.
Possibly.
Technically, would it be ultra?
Well, I think the other day we were looking at 10 to the minus 32 meters for the wavelength. Remember we were talking about that? Well, here our scale ends at 10 to the minus 16. We have to extend it 16 orders of magnitude. Actually, this one we'd have to extend it by 18 orders of magnitude out. 18 orders of magnitude out this way, which would give us what kind of light? Yeah, this would be, like we said about the 10 to the minus 32, that would be kind of the end of the world photon. Would this be the end of the world baseball? 60 miles an hour doesn't seem like end of the world stuff, right? And so then what kind of light is this? 60 miles an hour baseball is fine. That's not end of the world. So what kind of light is that?
UV. Could it be UV?
Actually, the answer is this isn't light, right? This is not light. This is matter. This is a baseball. Light, what is light? Light actually, light and matter are different because one of the ways they're different is that matter occupies space and has mass. Does light occupy space and have mass? No. Light has zero volume and zero mass at rest. Right? And so light and matter, light is energy, matter is the physical material of the universe. And so when we visualize this is totally different. This is what we can visualize. When we think about an electron is going to have some kind of wavelength. This wavelength is going to be about 24 picometers, roughly. Wavelength. Let's move along. If we have a baseball, that baseball is going to have a wavelength. The wavelength is so small. That wavelength is 10 to the minus 34 meters. You know, that wavelength. This is, you know, grossly expanded. 10 to the minus 34 meters. They're extremely small. That's the way I think about it. Now, when matter has wave properties, then we have to watch out for let me fast forward here. We have to watch out for this. And that is, let's take a look at a string. Obviously, string is going to have wave properties here, a string on a musical instrument. And so if we have a musical instrument string and we pluck it, then we see a wave. In fact, this is a half wave length here. And so L is equal to 1/2 lambda, a half wavelength. Now, if we pluck it harder with more energy, well, it turns out it doesn't absorb. You know, if I just plug it a little bit harder and just want this to be a little bit higher in energy, the energy is going down here. It doesn't work. I have to plug it hard enough that I can fit 2 half wavelengths in here. This is a standing wave or string. Because if I try to fit, let's say, 3/4 of a half wavelength in there, it's not going to work. Because if I try to fit 3/4, you know, the string has to attach on one end and has to attach on the other end. And so if I try to put 3/4 of a half wavelength in there, then the string would have to be up here. It's not going to happen. And since the string has to be attached at both ends because it's physically constrained by its size, I could put 1 half wavelength or I could put 2 half wavelengths, but I can't put anything in between. And so what we see is this. We see that strings are naturally quantized in energy. That is, this string will absorb enough energy to vibrate at this frequency, whatever that is, but the next frequency that's allowed will be double that here. That is 2 half wavelengths. And so when we look at the equation, we see this. The allowed L values are going to be n times lambda over 2, where n is an integer. From 1 to 2, the next allowed value will be n equals 3. And so L equals n times lambda over 2. The next one that will be allowed will be n equals 4. And n equals 5. Can I have a fraction? For example, can I have n equals 1.1? Is that possible? No, it's not possible. So here we see that strings like this are naturally quantized. Well, it turns out, let's imagine not a string here, but let's imagine an electron in here. And if we have an electron confined, we'll call this electron in a box. So we put an electron in a box. And the electron in the box is going to have wave properties. And because of the way the waves interact, we can only have certain wavelengths allowed. So let me go back here. And that is, if we have an electron in the box, we want this electron in the box to have what we call this constructive type interference. Because if the waves are slightly off here, we'll have destructive. And so this would be like a forbidden kind of state. Well, the same thing about an electron in the box. It would be similar to the string in that sense that that an electron confined in a box is going to be naturally quantized, because an electron confined in a box can, well, this is going to be a very small box. How small of a box would this be? Well, this box would be about 24 picometers. If we have a box about 24 picometers, then the first allowed energy would be 1/2 wavelength in there, this, right? What's the next allowed energy? If an electron is in a 24 picometer sized box, the next allowed energy would be where we fit 2 half wavelengths in there. And so we'd have to calculate what that energy is using lambda, right? What the velocity of that electron is. The next allowed energy would be in a 24 picometer size box would have 3 half wavelengths in there. And so this is a very small box. And it turns out that the atom is a very small box. When we look at the atom is on the order of 100 picometers, right? The wavelength is on the order of 24 picometers, let's say, or roughly. And so what we'll see is this, what's allowed is if an electron is confined to an atom, which we'll call the atom of the box here, then the electron is going to only have certain allowed energies. This being one of the allowed energies where the waves superimpose on one another. But here, this energy is not allowed in this size box because what happens is this. The electron has this wavelength, but when we go here, you'll see that it's offset, the peak and the trough. They just have to be a little bit offset. And when they're a little bit offset like this, then we have destructive interference of the wave, which means that this wave will cancel out. And so this would be a forbidden energy here. This would be an allowed energy here. And so this is what happens when the electron is confined in a small box. And so the way we can visualize this is this. If I'm looking at a baseball, is the baseball confined to a box? In a way, the baseball is confined to a box. Because if I look at a baseball, let's say you have the pitcher here, and then you have a catcher over here. And this person throws the baseball. This baseball has a wavelength of 10 to the minus 34 meters, 60 miles an hour. The catcher catches it here. All right, what's the next allowed energy of the baseball? The next allowed, well, it depends on how many half wavelengths can I fit in there. How many half wavelengths do you think I can fit between the pitcher and the catcher? A lot. I mean, because a half wavelength is only 10 to the minus 34 meters. And so what I need to do, well, that's at this energy. I need to bump this up in energy. And so the next allowed state for this baseball would be where I add one more half wavelength to this. Well, how many half wavelengths are there in this distance? Enormous number. We're talking trillions upon trillions upon trillions of half wavelengths. And so let's say this has a trillion, trillion, trillion half wavelengths. The next allowed energy would be a trillion, trillion, trillion plus 1. What's the difference between having a trillion, trillion, trillion versus a trillion, trillion, trillion and 1? What do you think the energy difference there is? Negligible. The energy difference, it's tiny energy difference, right? A tiny, tiny energy difference. Versus this. If I confine an electron in a box, well, the electron, well, if we think about it, what kind of box do we confine it? We confine electrons in atoms. Well, how big are the boxes for atoms? 100 to 600 picometers, right? Inside. And so if I confine an electron in a box, it's being confined in a very small box. Well, if it's being confined in a very small box that we call the atom, then we're going to have this. That's 1 allowed energy. And then the next allowed energy is going to have this. What's the energy difference between these two? The energy difference between these two is significant. There's a significant jump. We're going to see that this energy is going to be quite a bit lower than this energy here. This one's going to be quite a bit higher. But whereas this one, we see that, what's the difference between having a trillion, 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 and then a trillion, trillion, trillion plus one? Could we even really calculate the energy difference there? Yeah, we could. It's going to be extremely small. So this is why, this is the reason why people say about quantum mechanics, we're dealing with very, very small things because the wave properties are not significant until we get, like for example this. If we start shrinking this down smaller and smaller and confining the baseball to a smaller and smaller box, although we can't because the baseball is a big object, but let's say we can confine it to smaller and smaller, then it's going to make a difference, right? Because then there's going to be a big jump in terms of energy once we hit it to this. And so this is why we see that some objects are black bodies. For example, this. If we look at an iron atom, what we're going to see in an iron atom is this. We're going to see that they're going to be forbidden and allowed energies. And the spectrum will result in a line spectrum like this. A line spectrum, each line represents an allowed energy, and then you have the dark region between the lines which represent forbidden. And so, an iron atom would not make a very good light bulb because what we're going to get are only certain colors out of there, not the whole rainbow colors. But a piece of iron metal, what we see is a continuous spectrum. And so if I heat a piece of iron metal, I'll see the full rainbow colors. As a continuous spectrum. And so what's the difference between iron metal and an iron atom? In iron metal, the electron is confined. Well, actually, let's go to iron atom. In an iron atom, the electron is confined to a single iron atom. And so we have a situation where this is a very small box, and we have to fit an integral number of half wavelengths. So this is allowed, and so I have 3 half wavelengths in there. The next allowed one would be 4 half wavelengths, right? That's it. And so in the iron atom, the electron is confined to a very small box. But in iron metal, the electron is not confined to a small box. When I look at a piece of iron metal, let's show you a piece of iron metal here. This is a piece of iron metal here. How many atoms are there from this end to this end? How many atoms do you say? I'd say there are trillion, trillion, trillion atoms going from this end to this end, right? Something like that. It's a huge number of atoms, right? Now, is the electron confined to a single atom there, or is the electron free to move in the entire? It's free to move in the entire distance. And so what we have here is a situation in iron metal, even though the wavelength is the same. Let's say we have the exact same wavelength as in the iron atom here. But when we think about that, well, say we have this half wavelength, which is the same as that. What's the next allowed energy? The next allowed energy, let's say it would be a trillion, trillion, trillion plus 1 half wavelength, which is like that. And so we just make enough room for adding 1 more half wavelength in there. Is there much energy difference between those two? There's nothing. In fact, it looks continuous because the energy gap there is nothing. Whereas here, what's the next allowed energy here? The next allowed energy is going to be a big jump because we got to fit one more half wavelength in there. And so again, for quantum, it's not just for, you know, for large objects like a baseball, but it's also for electron. Electron's a very small object. But if you put a very small object in a very large box, then it's continuous, essentially, because a small object in a very large box, then the allowed wavelengths are just, okay, +2, +3, +4, you know? And so essentially it's going to look continuous. This is why when we look at iron metal, when it gets white hot, is going to emit all colors of the rainbow. There are no colors missing, there are no gaps, even though it is quantized. Whereas iron atom doesn't emit all colors. Iron atom is only going to emit certain colors because of these big jumps between allowed energy states. There's almost no jump here. And for a baseball, are there forbidden energies? Yeah, there's forbidden energies. We can't fit, you know, a quarter of an extra wavelength. It has to be a full half extra wavelength. But what is that, the energy difference there? The energy difference is nothing. And so the energy of the baseball can be continuous. And so this is the same thing. Somebody, you know, Noah was asking me about the sun. Well, you know, in the sun, you have what we call free electrons. Yeah, those electrons are confined to the sun, but how big is the sun? Huge. And so when we think about the sun, you know, and the electrons are part of the plasma there, the electrons are free to roam in the whole sun. So essentially the electrons are free. That means if we have free electrons, then does it matter? Okay, if I have a wavelength like this, can I add just a little bit more energy and get a little bit higher? Yeah, I can just add a tiny bit more energy and it'll be absorbed by the electron. Electron is free to move, and that's why the sun is going to be a good black body emitter, because the electron can have any energy it wants. Just like the iron metal is a good black body emitter because this electron, if I just add a little bit more energy, it goes here, that's infrared. If I add a little bit more, maybe that's red. If I add a little bit more, that's green, blue. I get the whole rainbow of colors because the energy gaps here, essentially, when I look at the energy level diagram, it's pretty much continuous because the spacing between the lines is next to nothing. Call this a band of energies here. Whereas in an iron atom, we have gaps like this in the energy spectrum. And so iron metal is a good black body. It can absorb a little bit or a lot. Iron atom is not a good black body. You know, it can absorb this much. Everything else is forbidden between there. So does that make sense? So this is why in macroscopic objects, the wavelengths are too small to notice, you know, any quantization of energy. It's just when you start confining it in very small objects, when the wavelength becomes significant. You know, here the wavelength is significant compared to the size of the atom. Here the wavelength is insignificant compared to the size of the baseball field. Here the wavelength is insignificant compared to the size of a chunk of iron. But it turns out that the classical physics was not wrong. You know, from quantum physics or quantum mechanics, you can derive all of Newton's laws. You just assume that you're dealing with large properties. I mean, not large objects. And when you deal with large objects, then you get the same exact equations as Newton did. Let's see what happens with the projector. All right, so what happened with Bohr? Bohr just postulated about these forbidden energies, but forbidden energies come quite naturally when we think of electrons having wave properties. Now, do electrons have wave properties? Now, wave properties for electrons, we'll take a look at here. We can see here are two water waves, you know, and somebody drops an object there, drops an object there. So we see the origin of two water waves here. And as the two water waves disperse from the origin, you can see that they interact. Here they can interact constructively, destructively, and they give this interference pattern that we observe here. We could set up an experiment as well with electrons. So we're still talking about the wave properties of matter. By setting up a barrier here with two slits. So this is called the double slit experiment. If we have a water wave would impinge on this. So let's say there's a water wave coming here, and the water wave would go through here and then come out like this. And the water wave would go through this slit here and come out like this. And where the two water waves meet, we'll get a pattern like that. Pattern where they interact constructively and destructively. You can see this pattern here. So those are wave properties. Now, what happens with electrons? We could do the same kind of thing and see, or try to observe the wave properties for electrons. So if I shoot an electron through here, let's say, well, the electron can go through this slit or through this slit, right? And then we'll have it hit a detector. There's some detector out here. And so that seems to make sense because an electron is a piece of matter, it has mass, right? It occupies space, is that correct? And so electron is either going to go through this slit or this slit, right? But electron also has wave properties. So the wave properties, well, if it has wave properties, then maybe if it goes through this slit, we'll see wave properties of that. But an electron does something funny, though. If you have one electron, you would think, okay, the electron's going to pass through here. And if the electron passes through here, and it's got wave properties, we don't expect any kind of interference pattern, right? Because it's just going through here, we aren't having a wave go through there, right? The electron goes through here, you know what results, though? An interference pattern. Now, why would that happen? And so, and how can you reconcile that? And so let's see. This didn't work this morning because the sound wasn't working, but the sound seemed to come back on. So let me see if we could see this. I'll pick the shorter one. I won't spend too much time. Dr. Quantum. The sound is working. You want to see it from the beginning, or no? We'll just see it from the double slit. Can you hear that? Not really, huh? Somebody's been fooling around with the audio, so I tried to get it back. But it's not working. Maybe it's a video. Let me see.
And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, are. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now, there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter, through. We get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange netherworld of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
So basically what you can conclude from that is electron is just Electron is like nothing you've ever, it's not like a water wave, it's not like a particle. So it's neither of those. Electron is very hard to describe because there isn't anything in the physical world that behaves like it. And so we'll just well, if you want to see what happened, maybe watch this next video here. But we're going to skip it. So basically, what we'll see is that here. We can see this interference pattern here, where it interacts constructively and destructively. So these are the wave properties demonstrated in some kind of pattern like this. Okay, the next thing that we have to talk about leading up to quantum mechanics is the Heisenberg observing principle. This also has to do with observing, but observing an electron. When you observe an electron, you observe it with light. And so when you observe it with light, what happens is it interferes with the electron itself. Because the light, even though it doesn't have any mass, does have momentum. And so a photon of light comes and strikes the electron. When it strikes the electron original trajectory is changed. So let's say the electron is like this. You observe it here, but now it's going to be moving this way. And so the analogy here is like if you're a photographer at a busy intersection. If you're a photographer at a busy intersection, you can pinpoint everybody, all the cars, all the walkers, whoever else, position by taking a photo. But what's missing out of the photo is, the speed that they're moving and the direction that they're moving this. And so we can pinpoint the position in a photograph, but we don't know the energy, that is, where they're going, how fast they're going. If we do a blurry photo, if we take one of those long exposure photos where everything's a blur, then we can see where everything's going. We can figure out the energy, but you can't pinpoint its position in that time. And so this is the Heisenberg. And so for us, the implication of the Heisenberg is this. We're going to pinpoint the energy, which is this term. That means its position is going to be uncertain. When we put all these things together, the quantized energies and everything else, we come up with the Schrodinger equation. Interestingly, this slide does not show the Schrodinger equation, even though it's mentioned there. But quantum mechanics, the main equation is the Schrodinger equation. Schrodinger equation is going to have this H term in here. It's going to be, H has a name to it. We're going to skip the name. There's going to be X, Y, Z parts. But nonetheless, we get the Schrodinger equation and we figure out the answer. So for the hydrogen atom, if you solve the Schrodinger equation, and it's not difficult to solve the Schrodinger equation, if we wrote it out completely, it would be a differential equation. Just with basic calculus of differential equations, you can solve it. It's not difficult. And so once you solve the Schrodinger equation, it turns out that for the hydrogen atom, there are an infinite number of answers. Well, if there are an infinite number of answers, do you want to write each answer out? No. Instead, what you look for is a pattern in the answers. And the pattern turns out to be a mathematical equation. And the pattern in the answer is this. The infinite number of answers, each answer is given by psi, the Greek symbol here. Psi tells us this, r theta phi, but we're not going to get into it. Psi is going to depend on, in the mathematical pattern, on three what we call quantum numbers, n, l, and m. Let's talk about that. And so each of the answers, infinite number, is going to show a pattern based on these numbers. And n is called the principal quantum number. 1, 2, 3, all the way up to a max of infinity. And that gives us our infinite number of The principal quantum number tells us about energy. You know, the higher the n, the greater the energy. And then there's the angular momentum quantum number. The angular momentum quantum number is given by L. And L is going to take on all values up to a maximum of n minus 1. So the pattern here is this. If n equals 1, what's my allowed L value? Well, it's all values up to a max of n minus 1. So it's going to be 0. And the max is going to be 1 minus 1 is 0. So there's only one L value. And so if n is equal to 1, L is equal to 0. L equals 1 is forbidden. If I had an L equals 1, that would exceed the max. For n equals 2, the L value is going to be 0 is allowed, 1 is allowed, but 2 is forbidden. 2 is forbidden because the max can only be 1. I mean, 2 minus 1 is 1. If n equals 3, then 0 is allowed, 1 is allowed, and 2 is allowed, but 3 is forbidden. And so this pattern will result in a new mathematical equation, which is the answer to the Schrodinger equation. But there's one more additional restriction, and that has to do with m sub L. But before I get to m sub L, L tells us the kind of the shape of what we call the orbital. And so L equals 0 is an s orbital, L equals 1 is p orbital, L equals 2 is d orbital, etc. L equals 3 is an f orbital. Do you know what L equals 4 is? S, P, T, F. Do you guys know these orbitals? S, P, T, F orbitals? Okay, what is an L equals 4? What kind of orbital would that be? First off, is L equals 4 allowed? L equals 4 is allowed as long as n is big. For example, if n is equal to 5, is n equal to 5 allowed? Yeah, in fact we have all of them all the way to infinity. So if n equals 5, then the allowed L values are 0, 1, 2, 3, and 4. So if L equals 4, what kind of orbital is that? It would be a G orbital. L equals 5 would be a H orbital. L equals 6 would be a I orbital. So we'll go alphabetical on that. For each L value, we have different M values. And the possible M values are going to range from minus L to plus L. Individual values including 0. So if L equals 0, then our allowed M value would be from minus 0 to plus 0, which would just be 0, one value. If L equals 1, then we go from minus 1 to 0 to plus 1. So there's 3 values that are allowed. If L equals 2, we go from minus 2 to plus 2. So it's minus 2, minus 1, 0, plus 1, plus 2. So we have 5 values. L equals 3, we have more values. Okay, so those are the patterns in the answers to the Schrodinger equation for this. But we look for additional patterns too. The additional patterns we look for is, since there are an infinite number of solutions, we want to recognize as many patterns as possible. And so one of the patterns is this. If n equals 1, how many L values are allowed? 1. If n equals 2, how many L values are allowed? 2. If n equals 3, how many L values are allowed? 3. If n equals 10,000, how many L values are allowed? 10,000. Is n equal 10,000 allowed? Yeah, n equals 10,000 is allowed. So if I had n equals 10,000, I'd have 10,000 L values. Can you list them all out? Yeah, you could list them all out. It just take a long time. You'd have 0, 1, 2, 3, all the way up to 9,999. Right? That would be the final L value that would be allowed. Now, if you have an L value, let's say my L value is 100. If I'm looking at L equal 100, how many M values would that be? It would be 201 M values. And so what is the pattern here? So if L equals 0, I have 1 M value. If L equals 1, I have 3 M values. If L equals 2, I have 5 M values. So the equation between M and L is 2L plus 1. 2L plus 1. And so I could figure it out. If I had L equals 1,000, it would be 2,000 N one M value. So it'd be plus 1,000, plus 999, plus 998, all the way out to minus 1,000. Now, the L values are called subshells. The M values are called shells or levels. And the M values are the orbitals. And so here, in the L equals 0, I only have one M value. And so that means there's only one orbital. And that one orbital is the S orbital. When I have L equals 1, I have the P subshell. And there are 3 P orbitals, 2L plus 1. When L equals 2, I'm in the D orbitals, and there are 5 E orbitals. And so let me ask you a question. How many orbitals are there in the H subshell? How many orbitals are there in the H subshell? $11? 11? Yeah, 11 sounds right because, you know, this would be the F, and so 4 would be A, B, C, D, F, G, 4 would be G, 5 would be H. So L equals 5 is H. If I have L equals 5, then I have 2 times 5 is 10 plus 1 is 11. I'm going to have 11 orbitals. What are those orbitals? Those orbitals are going to be minus 5, minus 4, minus 3, minus 1, 0, 1, 2, 3, 4, 5. That would be the 11 H orbitals. And so if we recognize these patterns, then we can generate all the allowed states, all the allowed orbitals for the electron. All of them. It would take an infinite amount of time, but we could figure it out because it's not hard. We could figure out all the allowed, but to figure out the energies would be a little difficult. And so this is how we build it up. We build it up using energy level diagram like that. And this is based on the quantum numbers. And so the lowest energy is n equals 1. Now this is for the H atom. For the H atom, we already know the energy. The energy of the H atom, E sub n, is equal to minus R sub H over n squared. Even though the Bohr model has been abandoned, this energy equation is still valid. This was empirically derived. And empirical does not come from theory. You know, so the theory might have changed, but this equation holds because this equation doesn't come from theory, it comes from observation. So this is why in formal reports we have a distinction between results. Results are your empirical observations. Those are never going to change because your results are based on observation. But the discussion, which is often based on theory, might change your interpretation of that. But when n equals 1, what are my L values that I'm allowed? If n equals 1, I'm allowed 0. Am I allowed any other L values? No. What m values am I allowed? Well, if L equals 1, the only m value I'm allowed is, m value is going to go from plus or minus 0 to plus 0. Minus 0 to plus 0 is 0. So I'm only allowed one m value. And so the first allowed state is what we call the 1, 0, 0 state. This is NLM, or the 1s orbital. That's it. How about, can I have L equals 1? No, I can't have L equals 1 when n equals 1 because that's forbidden. And so this would be the forbidden state here. The next allowed one would be an n equals 2. when n equals 2, I'm allowed L equals 0, that's fine. I'm allowed L equals 1, but can I have L equals 2? No. And so if n equals 2, then I could have the L equals 0, that would be 2, 0. If L equals 0, then my only allowed n value is 0. So I have one orbital here that's called the 2s orbital and the 2, 0, 0 orbital. But when n equals 2, I'm also allowed L equals 1. And so here I could have 2, 1. But if L equals 1, what are my allowed m values? Minus 1, 0, and plus 1. And so I'll have 2, 1, minus 1, 2, 1, 0, and 2, 1, 1. Each of these will be designated depending on how you draw the coordinate system. But what the difference is here is this. Those three orbitals look very, very similar. You know what the difference is? The difference is how they're oriented on the axes. And so we'll see it here. See if that's better drawn. So this is a difference. Each of these will have a different m value. So what the m value tells us is the number. There are three m values, so there are three orbitals. And the orientation. The orientations are going to be given by the minus 1, 0, and 1. And so these orbitals are going to be like this. You know, one of these orbitals will be the 2px, another one could be the 2py, and another one could be the 2pz. I have to look to correlate the numbers to the coordinate system, but essentially we're going to have the px, 2py, and 2pz orbitals. These orbitals are going to have the same energy. And so this is the 2p subshell, or the 2p set of orbitals here. Now L equals 2 is forbidden. The energy we can calculate. It turns out that all these orbitals have the same energy. When we go to n equals 3, we're going to get the 3, 0, 0, the 3, 1, negative 1, 3, 1, 0, 3, 1, 1. And now we have a new L value that's allowed. L equals 2 is allowed. And so if L equals 2 is allowed, then we're going to get the 3, 2, minus 2, the 3, 2, minus 1, the 3, 2, 0, the 3, 2, 1, 3, 2, 2. And we're going to get the 5d orbitals. These are the 3d orbitals, and there are 5 of them. The d orbitals also have designation to them as well. We can take a look at the d orbitals here. These are the 5d orbitals. They're all going to have the same energy. They just have different orientations. We call it the dx squared minus y squared, dz squared, dxyd, xz, and dyz orbitals. There's another pattern that we can start seeing develop. And that is for every n, how many orbitals do I have? So if n equals 1, I have a total of 1 orbital in this shell. We call it a shell. And so in the n equals 2 shell, how many total orbitals are there? There are 1, 2, 3, 4 total orbitals in 2 subshells. One subshell has 1, the other subshell has 3. In the n equals 3 shell, I have 3 subshells with a total number of how many orbitals? 9 orbitals. 1, 2, 3, 4, 5, 6, 7, 8. 9 orbitals. Okay. You know, this goes all the way up to what? What's at the top? N equals infinity. It's not that high. There's only, this is minus 2.179 times 10 to the minus 18 joules. This is 0 joules. And so in between n equals 3 and n equals infinity, I'm going to have a lot of levels. So let's pick one. Let's go to n equals 25. In n equals 25, how many subshells are there? N equals 25. I have the S subshell, I have the P subshell.
625.
So in n equals 25, I'm going to have well, not orbitals, you're right. I'm gonna have 625 orbitals. Those 625 orbitals are gonna be divided into how many subshells? The S is gonna take 1 out of the 625. It's gonna leave me with 624 more. The P is going to take 3. The D is gonna take 5. So how many subshells are there in the n equals 25 shell? Well, there's a pattern here. How many subshells when n equals 1? How many subshells when n equals 2? 2. How many subshells when n equals 3? 3. So what do you guess? How many subshells when n equals 25? 25 subshells, you're right. 25 subshells for a total of 625 orbitals. What are the subshells? Well, we can figure them all out, right? It just takes time. Let's go to n equals 1,000. When we go to n equals 1,000, which is allowed, how many orbitals in that? How many orbitals? 1,000,000 orbitals. 1,000,000 orbitals divided into how many subshells? 1,000 subshells. That's where we're at. And so we could figure these things out and build up a table like this. The interesting thing is this is for the H atom. H atom or 1 electron species. In the H atom or 1 electron species, it doesn't matter. If there's an electron in the n equals 2, it can pick any of those 4 orbitals. They're all the same energy. If an electron's in the n equals 10,000, it could pick, well, not 10,000. Didn't do that. If the electron is in the n equals 1,000 level, we'll take an electron, promote it up to n equals 1,000. It hasn't been ionized yet, it's still on each atom. But it can pick any of the 1,000,000 orbitals there to occupy because they're all the same energy. In fact, for a single electron, this is why, Bohr didn't realize this, but Bohr just said this is in the second radius, but in the second radius there are actually 4 allowed states. There's 4 allowed states. Well, what's the difference? We'll talk about that in a minute. But he didn't notice this because these are all the same energy. Energy only depends on n. Here. Well, when we get to multi-electron atoms, the energy depends on n and L. And so the energy equation gets a little bit more complicated. And why is that? Well, why that is we'll have to take a deeper look at orbitals. And so let's take a look at the orbitals in greater detail. Now the orbitals, well, this is mathematics. So when we solve the Schrodinger equation, we can solve it individually. There are 2 parts of the wave function, which we see combined. This is, do you see a pattern in all these equations, in all these answers? Do you see a pattern in there? Actually, there is a pattern. And the pattern comes out, well, these are individually solved, but if we didn't solve these individually, the pattern comes out that we can define all these answers by 3 quantum numbers. Those 3 quantum numbers would be n, L, and m. And so we can relate all these mathematical equations to each other because they're just going to have different n, L, and m values. That's it. And so what we do is we take all these answers and then summarize this into one equation. And that one equation, you take an infinite number of answers like that and summarize it into one equation. That one equation is going to have 3 variables, n, L, and m. And so you could do that in math. It's not hard to do. It's not hard to do. We just did the same thing. We look for the pattern and come up with some simple mathematical equation for that pattern. And that's how we get the n, L, and m. But it turns out the n, L, and m have physical meaning to it. And so we'll talk about that. Okay, from the wave function, we're going to get these kind of patterns like this. And what these patterns show is the shape of the orbitals. We have the s orbital, which is spherical. We have the p orbitals, which is figure 8. We have these d orbitals, which are like these cloverleaf shapes. And the shapes tell us something. Here's the answer. This this is the answer that you get. This is that R part is one of those equations, the Y part's the other equation. Both of those combined make the answer. And so this is the answer here. We don't see the variables that we need. We just see constants here. These are all constants. The variables are already factored in there. I wish they would have just showed this with the variables. But what is that? Well, the psi, which is the answer to the Schrodinger equation, is a wave function. This is the wave function here. And the wave function, that looks kind of funny, but it's the same thing as when we're looking at the standing wave. And so let me show you one more video here on this. So I had it up, 2D. I had this pyro one isn't so good, but this water one's okay. This one's good. They have one with fluorescent colors and other stuff, but we'll just take the basic black and white one. I think this is. Let me see if this one's good. Okay, these are 2D standing waves, so not all energies are allowed on this plate. This is this plate here. Okay, this is an allowed energy here. And we set up a standing wave here, so this would be a trough, and then there would be a peak, and then a trough. The trough is where the sand will settle. Okay, so then we go through forbidden. These are forbidden, nothing's happening. Now we have another allowed energy. And so you can see peaks and troughs. And then you continue increasing the energy here. It's allowed. It's forbidden, allowed. Allowed. So it jumps between allowed state and allowed state. Forbidden and then allowed, etc. How many of these would there be? An infinite number of these, right? And the only way you're going to figure it out is by looking for some kind of pattern in those. Yeah, that could be interesting here. So we have this. So this is the lowest energy one. So this would be the, and so the electron can be here. This would be the wave function for the electron here. And we see a positive amplitude here. So the sand would just make a circle around this, basically. That would be it. What this looks like in 3 dimensions is this, when we look at this. And what this is the answer to the Schrodinger equation. This isn't allowed. This is allowed energy, allowed state. Allowed state is we want to pinpoint the energy, so we know what the energy of this is. Well, the energy of this is minus 2.179 times 10 to the minus 18 joules worth of energy right there. But if we pinpoint the energy, what do we know about the position of the electron? It's uncertain, but it's not completely uncertain, because what we can do is we can square this wave function. When we square this wave function, what this gives us is a probability of finding an electron. So the probability of finding an electron is highest near the nucleus. But as you see, as we get further and further from the nucleus, the probability drops down. The probability doesn't go to 0 until we get to you know how far we have to go? Infinity. And then the probability will go to 0, so it converges at infinity. And so there's going to be a minute probability that the electron's way out here or all the way out towards infinity. But that probability is so small that we kind of ignore it. What we ignore is, there's very little chance. In fact, if we look at the volume of this, we take 95% of the volume of this. And then we see it's kind of small. So there's 95% chance of finding it within this volume and only 5% chance of finding it outside the volume. And then what we do is we represent that as this, the surface. So this is the 95% boundary. 95% chance of finding the electron inside this boundary, 5% chance of finding it outside the boundary. And so this is the representation of an s orbital. In three-dimensional space, in a box, this would be a hydrogen atom in a box, we see this. There is a chance of finding it outside of this box out here, but the highest probability is going to be right near the nucleus, and then it's going to drop down. This would be an electron cloud here. Okay. And so this is what we call the 100 orbital, or the lowest allowed energy for the electron. The next allowed energy is this. Now, we do something with the amplitude here. What we do with the amplitude is we color code it. And so this would be positive amplitude. The next allowed energy, which is the 200, unfortunately I don't have it. The wave function would look something like this, where this is the 0. Now the 200 is going to be like this. Whereas the 100, the 100 was like this, just positive amplitude, that was it. It didn't go drop. But the 200 is going to drop down from positive amplitude here to negative amplitude. And so this is color coded. This is blue, negative amplitude is red. And so what happens in the 200 is we get a wave function like this. And so what we're going to do is we're going to see this is the positive amplitude of the wave. And the wave is going to switch from positive amplitude through 0 to negative amplitude. Where the amplitude hits 0, we call that a node. This is a node in the wave. Okay, this is psi squared. We just square the wave function. And so a node is an area of 0 probability, finding that. But actually, this is not psi squared, this is psi. Because can we have negative probability of finding? Is there such thing as negative probability? No, the lowest probability is 0, right? And so there's no such thing. So what we have to do is we have to square this. But when we square this, do you know what we lose? What's the square root of 4? What's the square root of 4? Square root of 4 is plus or minus 2. Well, which is it? Is it plus 2, or is it minus 2, or is it both? Plus 2 and minus? No, it can't be both. It's got to be plus 2 times plus 2 or minus 2 times minus 2, right? But which one is it? You don't know, so you just lost that. You lost that. That's called phase information. We don't want to lose that. It's very important for us not to lose that. Since it's very important for us not to lose that, we color code it. And so the way we recognize that the amplitude of the wave is by the color coding system, because this is psi squared. And so this is our 4, and this is the plus, and this is the minus part. Does it make sense? Why do we need to know that? Why we need to know that is because when we mix waves, or when, like say we form a bond. If we form a bond, we want these waves, the orbitals, to overlap. When we overlap them, do we want positive amplitude with positive amplitude? Actually, we do. We want positive and positive. We want negative and negative, but we don't want positive with negative, because positive and negative will cancel each other out. That's forbidden. And so, are we out of time here? So this is why we're color coding this.